Right, so we're going to look at the question 3/109. We have uh, 2 kilogram collar is released from rest. Here, velocity is 0. A is the initial position of this collar, and then it slides down. This is the inclined fixed rod in a vertical plane, and during its motion, this collar is subjected to frictional force, and the friction coefficient between the collar and the rod is 0.4. So the engineering problem here is to calculate the velocity at strike the spring, and then the second one is to determine the maximum deflection of x until it stops, right? So when we talk about when we try to find the deflection, we understood that at that location, at that position, the velocity is 0. So this is the initial position, and then we have point B, which is we just label that position when the collar strike this position as B, and then after that with the energy that the collar has, it will stretch the spring towards C. So we have two kinematic states here. We are looking at two motion. In the first motion, we we would say that the the force acting on the body will be uh, different than the one that as the collar is moving to the second part, right? Now we're going to look at the first motion, right? As the collar is moving from A to B. So we are solving the energy equation because we are looking at two different states of the same particle. Right, we are given about the mass and the distance traveled. So S will be our coordinate system. We can also have X and Y. This one is X, this one is Y, right? So I'm using the coefficient matrix in order for me to convert the distance traveled by the collar in rectangular coordinate system. So and the angle is measured from the x direction, and it takes about 300 because here is 60 degree, and we express the distance travels from A to B, or position B relative to A, as 0.25 meters minus 0.433 meters. So the origin is taken at point A. Looking at the two states, so we are considering the energy of particles. So we are looking at the first motions from A to B, and we will using the free body diagram because we consider a single particles. Um, one way is to in this free body diagram, we're going to look at the forces that will act on the particles. We have weight, and we will obtain the component along the fixed rod, which is tangential and we are looking as well as the normal coordinate system, because the normal coordinate systems, normal direction allow us to determine the component which is parallel and opposite to the reaction force or normal forces acting on the particles. So we are using the coefficient matrix, and from the tangential direction toward the absolute resultant force due to the weight is 330, and the weight is given by uh, is 19.6 Newton. We are taking gravitational acceleration as 9.8, and from here we obtain the weight vectors, the force vectors in the tangential normal coordinate system, which is 16.97 and minus 9.8 in normal directions. So when we look at the based on this Newton's law, we can calculate the reaction force, which is 9.8, acting in the positive um, en direction, normal direction, and then we have friction, which is opposing the motion of particle, which is 3.92 newtons, and the weight component here is referring to the component of weight along the tangential directions. And then in order for us to evaluate the net force acting on the particles, we have the weight, which is in positive tangential direction, and friction in negative tangential direction, and we get about 13.054 newtons. Using the work energy methods, we can find that the total work done um, by the um, particles is given by the net force time the distance travel from A to B. We get about 6.5 joule, and we can calculate the kinetic energy at B. The book used 2 as the final position, and this is a work done by the uh, external forces and the body forces plus the kinetic energy at A. So here we can get the velocity of the particle at B, which is 2.55 meter per second. And similarly, we can use the energy balance. So we first calculate the changes of potential energy is given by this equation. Is definition of potential energy. Then we get what minus 8.49 joule, and then this is the expression for energy balance, which is changes in kinetic energy and changes in potential energy, which is equal to the net work. um, and then this work is used to the energy of this particle being used uh, to resolve all the energy from the surrounding, and the work done by the particle to the surrounding is given by this definition for um, force dot product as distance travels. We get about 1.96 joule, and then we can calculate the kinetic energy uh, changes plus the potential energy changes equal to work done by the particle to the to resist the frictional force, and from here we can get same amount of velocity of the particle, which is at 2.55 meter per second. And the next stage is to evaluate the velocity of to get the stretch length of the spring. First, we look at the position vector from uh, B to C, and then we get the position from A to C after we obtain the uh, in order for us to evaluate the stretch of the spring. From here, we evaluate the distance traveled from B to C. So what I'm going to show you here actually, what the total length, right? Which is required by the particle to move from A to C. But in the calculation here, we would like to know the distance travels from C relative to B, and then we get the expression for the distance travels, which is 0.5, the maximum stretch in x direction, minus 0.66866 of the maximum the stretch of the spring in y direction. The reason we are using the rectangular coordinate system because we can evaluate the potential energy and the work done by the gravitational force. Similarly, in the first motion, kinematic motion, we divided the force into the tangential and normal using the T and N coordinate system, and we find the work of the spring force acting in the opposite direction to the motion, which is parallel to the frictional force. This additional force um, exists during the B to C position. I'll just use the energy balance approach. So we can find that from the definition we have the total energy of the particles equal to the net work done on the particles. So the frictional force, not only by the spring force, which is the force by the spring, the definition is half kx, right? And the distance traveled is the maximum stretch minus 0 because at B the stretch is undeformed, so we get about 800 times the maximum stretch power of 2. And then we have the frictional force we had calculated before is 3.92 of the maximum stretch, and then we have the net force, which is 800 minus 800 maximum stretch power of 2 minus 3.92 of the maximum stretch. So we can get the potential energy change is given by this definition. We get about minus 17 maximum stretch. Here we just have this information, we plug in into the energy balance. So the final velocity is 0. D is the velocity at B, and then after we replacing all these total energy change on the right hand side, we get this quadratic equation. And in order for me to factorize this equation, so I'm using this software online root finder software from xrjunkie.nom.es, and from that we can get the real roots for this equation is minus 0.897 meters, and the maximum stretch is 0.913, so we are using the positive value.